Okay, we are recording. So thanks everyone for joining. It's my pleasure to welcome Johannes Brandstetter to our knowledge sharing session today. Johannes currently heads the AI for Simulation group at NXAI, a prominent European AI hub noted for its innovative contributions, including the recent development of xLSTM. He's also a group leader at the Institute of Machine Learning at Johannes Kepler University, where he works under the guidance of the renowned Max Welling. Previously, Johannes made significant strides as a research scientist at Microsoft Research AI for Science Lab, and today he'll be sharing his insights from his work on geometry-informed neural networks. So with that, I'll hand it over to Johannes. Looking forward to the talk.
Yeah, thank you very much for the introduction. Thank you very much for the invitation. So I tried to make this a bit like interactive, so I have the control over my slides and over the time, so to say. So you can, if there are questions, you can interrupt me and we can discuss on the fly. I will, before going too much into geometry-informed neural networks, I will give a more general overview of the field of PDE surrogates and surrogate modeling in deep learning, because I think this is one of the let's say highly hyped fields, which still needs a bit structure and where it's really hard to understand where research is going. And I think it's very important to speak a common language here. And in the second part, then I will more dive into geometry-informed neural networks. And regarding that, depending on how the time goes, I will go deeper or stay a bit more shallow. So I will start with something which is very personal to my heart, namely the speed in deep learning. There's lots of papers, as everyone knows, and there is lots of hype around different fields. And it sometimes it's worth to take a step back and look what is going on in other fields. And I recently was in the Easter holidays. It was my first time that I visited the CERN lab in Switzerland, where I did my PhD. It was the first time being back there. And I was really, really shocked how slow things move there in both ways, positive and negative. And you really, I mean, clearly there is still my sign on the door, which is definitely, yeah, how administrative slowly things move. But also, of course, to get new physics results, it takes you, basically you have to build a new accelerator with billions of dollars. Similarly, you can see that in nuclear fusion, which is another of my very big interests. There is like groundbreaking research done, especially in the UK, but to really get new progress, things move in terms of tens of decades and not months and weeks as in deep learning. And this is really the field we are moving in. And yeah, I said that because it's an introduction, because I think it's very important to just have the scale we're in, because we get these new papers out every day, and we are flooded on Twitter and social media and an archive with like 1,000 new papers every day. And it's really hard to digest that and to make sense what is coming in. And also many of these fields are just flooded, and it's really hard to get the structure. But it always turns out the longer things work or the longer things are in place, the more structure we get. And it seems really there's this big scheme. And first we tried to build deep learning architecture, started with the ImageNet revolution. Then the architectures were taking more and more place and more consolidating themselves with the introduction of transformers, where we started to unify architectures a bit. And then in the end, we went to large language models about 1.5 years ago, which is really the new frontier of scaling and enabling new capabilities. And these LLMs are really the driving force. Needless to say, these LLMs are what excites most people, where the money is flowing, why we have this restructuring in the companies, all these positive and negative effects. You all know so much and so well about these LLMs. The thing which is really interesting about LLMs, I think, in general about also large vision models, is this scaling properties. So we have the scaling laws, which tell us that if we increase the number of parameters and the number of tokens, we get a log performance improvement, which in the whole area of deep learning, which is quite some black box modeling. This is really a law which seems to hold and which companies bet billions of dollars on. And this is quite surprising. And yeah, of course, I'm from Austria. We're in Austria. I can't help to talk about the LLM, which we're introducing, the xLSTM, so the extended long short-term memory, which is our version of tackling these steps. I don't want to put too much emphasis on the slides. For those interested, you can read the paper. You can observe how this is going. Definitely, it's a nice side frontier I'm partly fighting with. But my main focus is definitely on the language of science, and this is, I think, what most of you are also interested in, and why I'm invited. And the language of science, we all know, is in some way is PDEs. So it's either in its simplest form is ODEs or stochastic differential equation, or PDEs. And throughout my life, or my career, I worked from very left to right. I started in high energy physics, which is at the scale of 10 to the power of minus 22 meters, so really tiny. We speak of nanometers, so to say. There is this famous standard model Lagrange, which every geek now and then should have on a t-shirt at least once in his lifetime. And from that you can deduce all the equations of these different particles in these different fields. For example, the Higgs field, or the gluon fields, quark gluon plasma, quark quantum chromodynamics, or whatever. But then you go towards some larger scale, which sounds a bit ridiculous, because you go towards molecules and modeling atoms and electron clouds. And this is the Schrödinger equation. It's standard form, where the potential is the V term here is the hard one. And I think a big hype is in classical chemistry. Nowadays, discrete molecular dynamics simulation, where a lots of interest is, or lots of money is going in, and lots of companies putting a lot of emphasis there. And I think in that sense, also like AlphaFold, I would put in a bit in this category. Then we come to fluid dynamics, and they're always driven by Navier-Stokes in its very different forms, in all its glory, so to say. And this is basically where I got. I never got to general relativity, although I have to say this excites me a lot, and I might force some students to start looking at this with me, because these equations is just so intriguing. The difference in general relativity compared to all others is that we have a space which basically tells the masses and energy how to move, and masses and energy tells the space how to curve. And this relation of geometry or curvature and masses energies is very intriguing, also from a machine learning point of view, because you suddenly have a response, so to say, to your surrogates, to your whatever you use to model that, and those inflict each other, whereas normally you have a static geometry or static environment. So it might be that we try something in that direction at some point. And when we talk about PDEs, I think it's, for me, I have this very simple, naive formulation in my head, because most of the time we talk about time-dependent PDEs. Of course, if we talk about describing geometry, it comes more into the time dimension is not so important. But usually, if we describe dynamics, we have something time-dependent. And time-dependent always means you have some derivative with respect to time, t, of course, and a lot of derivative with respect to spatial domains. And these spatial domains the spatial terms can include diffusion terms, convective terms, or similar terms. So we have this, and no matter how many orders, if you're second order in time derivative or even third order, one can always somehow rewrite the equation that one has the first order on the left and the higher order terms on the right. And what people then do is they estimate the right side of these equations. They estimate it via some finite difference, finite volume, and so on and so forth. and then they update the left side. And this is really how I imagine doing PDE modeling or general modeling of simulations. You can either estimate the right side by some neural network, then use some classical schemes to estimate the left, or you can estimate everything at once. For example, in weather modeling, you estimate the next state of the system, whereas, for example, in molecular dynamics, you estimate the forces of the different atoms, and then you use some integration scheme or some MCMC method to go to the next state. There is something which is really, really, really interesting in this area, and this is the interplay between numerics and like experts in this domain may be computation fluid dynamics, may it be geometry, may it be topology, and deep learning. And because it's this overarching problem that if you come from deep learning, you basically have this intrinsic need to tell everyone or to believe that you know how to do things, how to change fields. And if you're in a field, you're a bit reluctant towards whatever comes from outside and whatever might or might not disrupt your field. And the truth is somewhere very much in between. Deep learning folks have to know a lot of, or get to know a lot of domain, or acquire a lot of domain knowledge to really have an influence. And on the other hand, deep learning will or can have a lot of impact and can change and will change different fields. And so the overarching question is always the same: can deep learning really help? Where can make it a difference? And what does it take to do so? And this is not always so easy. So for the first part, I will be very computation fluid centric, because I think this is what is the easiest to understand. I think one question here is to ask, and this is now gets a bit more related to geometry, is the role of inductive bias. Because inductive bias is something we are fighting in machine learning on two fronts. There's the one front, this is the Erlangen program, geometric deep learning program, which formulates geometric deep learning as learning on grids, on groups, on graphs. So really learning on grids and on groups. So if this representation is a group, how you learn on this group. On the other hand, the transformer part, I don't know how to call it, everything is about scale and everything is about scaling up and encoding things such that the transformer understands it. The idea here is really, if you put that to physics, that all information is in the data and the scaling just comes with the amount of data, and the transformer learns what is physics and what is invariant. There is everything here is really on the data side, understanding the data, encoding either symmetries in the data or encoding whatever information such that the transformer knows how to speak. And there is a bit of a discrepancy in between these fields. I mean, you might have read the AlphaFold paper, and they put very prominently in the paper, finding no invariance and no equivariance is helping. That is, in my opinion, and I'm talking to a few insiders, really related that geometric deep learning people claimed the success of AlphaFold or previous AlphaFold very much in geometric deep learning. So you already see that there is a bit of a hustle here. The nice thing is, if we go to PDEs or similar fields where we can really write down our constraints, like diffusion is a second derivative with respect to space, divergence is the gradient times, or the gradient of Nabla times the field, and so on and so forth. We have our very, very, very explicit constraints. We don't have to learn on groups. We don't have to learn on grids. We can really specify our constraints. And these constraints, they somehow translate to knowledge, and knowledge somehow translate to data. So this is not implicit, but it's really explicit knowledge. And therefore, I very loosely put these things into physics-informed neural networks on the one hand side, constraint-driven learning on the one hand side, and operator, which is data-driven on the right side. There is many things in between. It's very hard to really find a boundary, not like a rigorous boundary. But for an understanding, I think it's easy to think of these two parts of the coin. And we will start with the left side. No, sorry, I start with the right side, because this is the data-driven, and this should be the prelude. And this is the field of neural operator learning. This is a very, I would say, hyped terminology, which in the end just means that we are dealing with continuous signal and how to present this continuous signal to the neural network. Because if you think of weather, you have a continuous state of the weather on the Earth, and you have to somehow discretize it by taking it into account that if you pick different points on the Earth, you definitely have to, this lives under a continuous field assumption. And you very easily can recognize that if you sample different points means they can be at different grid locations, or they can be just the number of points can be different. You somehow have the same underlying field, and that needs to be taken into account by the neural network. And that is basically the whole gist of operator learning. There's lots and lots and lots of theory papers and many fuss about that, but in the end, everything is then related on a grid and on some regular data, which defeats a bit the purpose of why this is introduced, because operator is really the principles which we need in physics to scale to larger systems. And one of these examples is weather modeling. Since I think 2 years, we see a rapid rise of these neural approaches, starting with ForecastNet from NVIDIA, going over Pango from Huawei, GraphCast and GenCast from DeepMind. I should say all of these papers, all of these models operate on a 25-kilometer worldwide grid, which corresponds to some resolution of 1,400 times 700, and then times some vertical levels, and then times a lot of variables. So this is very, very, very high resolution data, corresponds to approximately in the order of gigabyte per data point. So each data point has the size of a gigabyte. So this is very, very challenging and demanding. And towards this end, I want to be a bit personal. So my understanding of science, deep learning for science, started to shift with this paper. So that was a paper we did like 1.5 years ago in Microsoft. It was for me a bit of a paradigm shift in the following, because the research question was that humans model weather and climate since decades. There's like so much petabytes of data stored that you can basically train a model forever. So why not somehow try to get all this human knowledge of data into the neural network by pre-training just on simulations? And that should be good enough to get everything, every human bias you can have into the network. So not encoding something like energy conservation, mass conservation, or whatever, but just using simulations and trying to make the network aware of all these simulations. I was a bit hesitant starting this project because I always thought that it's in the end the inductive bias of neighboring regions, of energy conservation, and so on and so forth will help to scale these AI models. But doing that really changed my way of thinking, and I got a big fan of these ways of doing this AI for science, and this way of doing AI for science. And in fact, I got such a big fan that I was really voting to scale these things up. Bit disappointed to don't see the enthusiasm around me that I had, but I'm very happy that Microsoft managed to pull this off. And we have this paper which called Aurora, and which is doing the scaling this up. And instead of training on one data set, Aurora trains on a variety of data set, on a plethora of data set, and on like highest resolutions. And it's the first model to outperform numerical weather forecasts at 10-kilometer scale. It's the first model to really show the scaling behaviors. It's the first model to do some environmental forecasting. It's the first model to predict like storms and extreme events, like days in advance. And it's super cool, and convinced me once again that this is the way to go. Although I have to say, of course, I was in the end only passively involved, but I very much like this approach. And what personally got me a bit going is to extend that towards other domains like particles, mesh-based systems, and all different kinds of simulations. And in doing so, I basically found different ways what is important here. And most of the time, or the most important question is scalability. How can we scale this method? Because if you think of all these particles and all these simulations, then it's the research question number one is, how can we encode this different knowledge? How can we encode this different number of particles into our system? How can we make that scale if we take different data sets into account? So we need something like a latent space, a reduced latent space, which takes up this information and which allows us to go forward. I'm not going too much into detail, but I think that the message I'm trying to bring across is we need a flexible encoding, similarly to what we do in weather. We need to do in the simulations. It should be flexible across geometries. It should be flexible across simulations, and should be flexible across data types, be particles, be grid-based methods. And if we then start to basically look at the landscape of current models, we can either use GNN, but what is printed here on the X scale is on the X-axis is scale. So 1 corresponds to 32,000 nodes, and then like this number just scales with the factor here on the X-axis, and we see that the memory footprint of transformers, like linear transformers, even in GNNs, is just insane, and it doesn't go to large number of systems, especially if we think in this scale of weather or going beyond, and also that the state-of-the-art algorithms are not scaling very well. And this is our method, what we are trying to, or what we introduced, and this is like a much better scaling behavior in terms of the memory footprint, because even for 500,000 of input points, we easily fit them on a GPU, and I think this is very much preferable in this area. And just to give an idea, last overview how this scaling should look like. I think that the main important part is that you subsample your input such that you have a reasonable representation. It can be across like geometric representation. It can be across number of particles. It can be across meshes. We show basically different ways of doing that. And then it's important to aggregate information locally, because that's the only way which scales. You can message pass locally, but never across the whole graph or the whole input representation. With that, you have already an aggregation of the messages, of the information very locally. No matter if you learn on geometries, if you learn, for example, in tokamak plasma physics, if you learn on the world on different weather stations, you always need to extract information locally. And then you have this local information, and then you basically need to treat them as tokens. And this tokenization is what we all know from vision transformers and from language modeling. And on this tokenization, you can use transformers. But since this input will be very high dimensional, this is still will still be very high dimensional latent representation. So we can then compress to a really compressed latent space. And this latent space should have the same dimension no matter how many input points we have. And this is easily done by basically having the final compression telling how many latent tokens we have. And there are tools from computer vision which are used in multimodal representation learning, which tells you, okay, I want to map to this latent representation. And here in this latent representation, what we're adding is all the auxiliary information about physics, geometry, and whatever you have. And this is very much the right side of this geometric deep learning versus transformers, because in the end we still add all the information we have, because each physics information is important, but we add them like either with sine cosine embedding or conditioning the architecture or whatnot, and we add it in the latent space. And the encoder has the information, or has the task to compress the scenario to this fixed representation. I'm not going so much about the architecture here, because I think this defeats a bit the purpose. I think that the overall picture is much clearer. But I want to say one last thing about, before we go to geometry-informed neural networks, one last thing about these operators, because as I said, we always have this comparison against numerics. And one thing neural networks should be able to do better than numerics is scale. Because numerics, they always, if you go to large number of particles, larger simulations, larger number of grid points, higher resolution, at some point numerics get extremely compute intensive and it blows up. And this is something what neural networks should have a better scaling. And that is something which is called discretization convergence. Discretization convergence means that if you have different number of points, of input points, you basically have the same error. The error is not blowing up. And this is exemplified here in this upper right plot. This is some computational fluid dynamics simulation, not that important, but these simulations are done on a mesh of about 100,000 mesh nodes in 2D, and the orange ones are some obstacles which are sampled arbitrarily. And we are really training on it by choosing between 16 and 32,000 mesh nodes arbitrarily in the input and output. And then in inference, if we increase the number of these nodes, if we go to, or decrease, go down to 4,000 and increase, go up to 32,000 or larger, the error stays the same. So the network learns this representation based on the number of nodes you're giving. Of course, if the resolution is too coarse, then it worsens, because then you just cannot resolve some phenomena. And if the resolution is too high, then you cannot again resolve some phenomena internally. But in this wide realm of some orders of magnitude, the neural network is really able to capture that. And this is, I think, one of the biggest advantages of these neural models. And the second one is that these models must have something like scalability internally. You can think of that if you have fixed number of tokens, but also in inference, you can increase this number of tokens as you can increase the context size of your language. This should make the model just understanding more, but the complexity, of course, explodes if you have a larger number of tokens, which makes it much harder to model these tokens. But you can do that in inference. In inference, it doesn't matter if one forward pass takes much more time. But again, this should not degrade the performance of your neural network. And that is what is shown here in this plot, that this is the number of these latent representations. So in inference, we just blow these latent representations up, and we want to have similar performance. I'm showing the slides not so much about promoting this work, but because I personally think that these are the measures which are super important if we scale such simulations and if we go towards larger simulations, being particles, being mesh-based simulations, being simulations in geometries, being simulations of different systems. We need this discretization convergence both on the input and output domain, but also on the architecture. And this is something, in my opinion, very much overlooked, because it's very hard, and it requires a lot of compute. And you can only really think about that if you have compute and if you think of scaling. But in the end, if you want to introduce something which at some point is going to be a real replacement or a real competitor to numerical methods, these are the questions to ask, in my opinion. And then this arises to the second extreme. What is if you don't have data, or if you don't have enough data? And this brings us to physics-informed neural networks, theory-informed learning, which I think you're familiar with. And the idea is totally different to the transformer area, because you really use scientific knowledge to eliminate inconsistent predictions. This is also, again, different to geometric deep learning, where you use like superficial ideas about symmetry, superficial ideas about manifolds on which the data lives to reduce the search space of the network. Here you use precise scientific knowledge, precise equations to eliminate this knowledge. The most famous examples of physics-informed networks, which take a boundary value problem and write it down as a constraint violation. You have an ansatz function, you input some coordinates, the ansatz function has to obey the PDE at hand, and it has to obey the boundary conditions, and this is what is giving the loss which you're trying to minimize. So you really learn a physics model which obeys the equation at hand by really learning to fit the constraints. This works kind of not. It's a bit, I would say, disputed how well pins work, how well pins generalize. I think they are a brilliant idea in terms of being the first model to learn data free. I hope a lot of more is coming in this area. And something which we are doing is the geometry informed neural network approach. I think today is a funny coincidence because we started promoting it today. It's driven by these brilliant people, Arthurs and Andreas, and they just went one step further. They said, okay, we have it in physics that we can write down our PDE and our network which fulfills these constraints. Why not use something similar in geometry? You can write things down as a function. You can write things as a function constraint, because you, for example, if you have an interface, so for this chat engine is detached at these green points, we can tell the network it has to be 0 at these green points, because it is where it is attached. If it is larger than 0, we violate it. And what does it mean? We violate it. The it in that sense is a neural field, so it's a function representation of this geometry. So what is a PDE will be a function constraint in geometry. Getting these function constraints right is really hard, but there's one very, very fundamental difference with respect to PDEs, and that is the underdeterminedness. So usually in geometry or in general in these tasks, you have underdetermined systems, meaning that the system has infinite many solutions because, well, it's underdetermined. So diverse solution is a good thing. You know from this engineering topology optimization contests, there's many solutions, and best one wins. So in contrast to pins, what we really need here is not only neural networks which obey and which satisfy these constraints, but which are also giving diverse options, because this gives a broad range of applicability. I should also say that this is a very, very new field and a very new way of thinking, and it's very much that this is not leading anywhere, because in the end we won't be able to really outperform some numerical methods. But on the other hand, it's also very exciting since this starts to give a very new direction of where this is going. And this is also why I tried to bring this operator learning on the one hand, which is so heavy data driven, and where scaling is the big problem. And here it's more really learning to understand the constraints and learning how to write down these constraints, because in the end we will be measured how well we've written down the constraints. And the better this constraint is written down, or the more the constraints we have written down, the better we can make our network behave. So one example is shown here, where we basically see that the training progress of fitting our geometric informed neural network to these interfaces, being in a certain volume, having a smooth surface, and so on. So we're asking ourselves the three questions. The first one is how are we going to represent the shapes? The second one is how do we enforce these constraints? And the third one is how we introduce diversity. And these questions put us in this intersection of these three parts. So we have the neural fields on the one side, which is really taking off in computer vision. We have generative modeling. Well, I don't have to say much about generative modeling. And we have theory-informed learning, which is not so big. And on the interface, these are sitting the chins. So they have this generative part due to the underdeterminedness. They are both neural fields with pins. Writing down the constraints is very, very different though than for pins. And I think before like really basically going, or instead of showing how to write down these constraints, I just show a few examples. So on the left, you can think of this minimum surface, and we have put up a notebook where you can basically generate this in like seconds. What you have given is the green part, and this is the interface, and then you have the condition of zero mean curvature. And zero mean curvature, well, is just a measure to get minimum surface, and you can write that down. I think it's even in the table here, mean curvature, exactly. So you can write down these function constraints as the divergent of the gradient of the function over the norm of the function, and then you can optimize on that. And what you get out is a neural field which has the value 0 wherever we have this gray area, and is larger than 0 everywhere outside. So you basically, if you then plot 0, you have found this this neural field obeying these constraints. Similarly, you can ask a mirror basically to reflect within one point, and what comes out is this gray, this black line. It gets a bit more complicated if we look at this example on the right. So what we have here is an obstacle within this design region. So this design region is everything which within this shaded area. It is connected to the left and the right, what we call interface, and it has to basically has to avoid this dot in the middle, or this obstacle in the middle. What happens here is, of course, there can be multiple solutions, and we are enforcing this solution via explicit diversity term. And then we can interpolate in the latent space, and we get these nice different solutions morphing into each other. And this is something I found very intriguing. What should also say, this is 2D. I mean, this trains very nicely, but this is still 2D, and it's far a long way to go to get this to 3D, to get these 3D simulations or these 3D shapes really fast. The training takes 1 day. I think this can be sped up to minutes or even seconds, but this is a long way we have to go. But the principles we already see very nicely in 2D. And finally, what I like a lot is generative pins. So we can again look at physics-informed neural networks, and there is this nice reaction diffusion equations. So you have this two different liquids, so to say, and direct and diffuse regarding these terms. And one can write down for a certain set of parameters, one can write down this equation and solve this with pins. There, of course, pins give solutions to that. But what we can now do in physics, of course, you first get your general solution, then you determine your initial conditions, and then you can get your specific solutions, so to say, a particular solution. But what happens if you don't have initial condition? Then you can get any number of solutions. And that's exactly what we're doing here. So we don't give initial conditions, we just have this violation constraint, and we enforce diversity. And then we interpolate in the latent space, and we get the different solutions which we can smooth into each other. And this smoothing into each other is what basically translates to choosing or picking different initial conditions and using these different initial conditions. And that is really for us the first real connections between physics-informed neural network and geometry-informed neural networks. And this opens the door to many different applications in a way. So first, we want to understand a bit better what we can do with geometry and physics, how we can use more knowledge from the one field and the other field. Secondly, usually simulators will be replaced by neural operators. So whereas you usually have your geometry and you interact with your simulator, you will have now some neural field interacting with some neural operator at some point. So we have to understand how that translates to each other. Thirdly, we have geometry as a very, very important point, as a very important representation, which is in one hand an ingredient for neural operators to model physics system. On the other hand, has to be understood in terms of constraints and violation to model via neural fields. So I think this opens up a whole new area of research by treating this data free and data extreme place or fields not as very distinct, but as something very interconnected. And that is the last slide. I tried to be to have enough time for question and discussions. So I will leave the floor here for you. I can't hear you.
Yeah, work away, Nima.
Yeah, thanks a lot, Johannes. That was very interesting and also super dense. I have a couple of questions. Let's go backward in time. So this maximizing diversity, what's the intuition or physical reason behind it? I didn't get what was the motivation there.
Yeah, it's a good point. I mean, I didn't have written down the equations because I don't feel they are very meaningful. One can read them up. But in the end, it just means that what the network produces for different latent space conditions should be diverse. So you for example have a latent space of, I don't know, 256, and then you have some extra neurons, so to say, which similar to the variation autoencoder have some random values. And then if you change this latent space structure, you should get diverse solutions. That's what's called a conditional neural field. You get the solution, but depending on some latent representation, and if you change the latent representation, you want to have a different output. And we basically encourage the network by putting a loss on the different outputs. So the different outputs should fulfill all of them should fulfill the constraints, but each batch, so to say, should have a diversity separation.
I see. Okay, so it would not basically go to, like, I don't know, obvious solutions like every field is zero and
I mean that would of course be that happens on the left and in the middle here, but there's only one solution. But if you have something with here on the right, there are infinite many solutions, and we think that the real power comes that the network is able to produce a lot of diverse solutions, which many numerical tools cannot do.
Thanks.
And it's also personally a bit funny to produce something generative without having any data. That's the like scientific intuition.
Yeah, Nico?
Okay, I have a question. Do you see a future for like thinking fast and slow like approaches where you do the bulk of the work in a neural setting, and where there are issues in the neural setting, like around difficult boundary points or something like that, you resort to numerical methods and like combine basically the strength of both with some sort of decision-making framework to decide what part of the problem to solve numerically and what part of the problem to solve through fitting models?
Yes, that's a very good question. So I personally think that neural networks will never replace numerics, because that's just silly. And you always need numerics in one way or the other, and just speed for getting training data. It's more like neural networks will augment numerics. So at some point, I think and that's what I try to do here at scale, ask questions, where is numerics breaking down? And then how neural networks can help. I really think that neural networks, if they just work so different than numerics, they are precise, they are stable, we know how to do discretizations and so on. Neural networks, they're wild, they're not stable, but they are fast and they can generalize. And different, since they're so different, they just also work for different problems differently. And this is, I think, the great power we see here. So For example, one is always doing PDE simulations on regular grids with periodic boundary. I did the same stuff in many of my papers, but it defeats the purpose, because this is where numerics is perfect. One has to do simulations at boundary regions. One has to do multi-flow simulations. One has to do simulations where we interact with, I don't know, discrete element methods versus computation fluid dynamics, and so on and so forth, because this is what is hard for numerics. So yes, I fully think that we will have to tackle this problem of so to say combining these tools. I don't know if this was a good answer, but I tried.
Thank you.
Can I ask another question? So this is maybe a little bit technical. Can you go forward, please, to your page 22?
Sorry, 22?
Page 22, yes.
I don't see the pages. Oh, yeah, no.
Oh, you see. Go further at the end of this. Here, in this case of that you aggregate global information, that's a little bit puzzling for me. So here we would lose the spatial information. Or how does
very good question. So we can go a bit more into detail here. So think of this really as it is. So these are only particles, right? But what we see here is particles, and each of these particles has a velocity vector. So if we just go through that, I think it will be clear. And what I'm saying is that neural networks don't need to have this fine graining as numerics do, so we can subsample. But even if we don't subsample, that's not important. Then we aggregate this information towards some nodes. And that means basically each node transports information to another node. So nothing is lost, just information is aggregated at some nodes. So this is the black nodes here. They still correspond to all the nodes. And these nodes are then, so to say, seen as tokens. So these nodes, they have some positions attached, and we can then see them as a sentence already. So that in that case, we have basically transformed the whole system into this latent space representation of tokens, which are used in a transformer nowadays. But the thing is that usually if you have many number of particles or many mesh points, you will have many of these nodes, and you will have a very long sentence, and talking about tens of thousands tokens or hundreds of thousands tokens if you go to large systems. But usually the information these tokens is very similar, because neighboring tokens they have not so much different information. If you think of a language, of a sentence, where each token has a really different meaning, so we can really down compress these tokens again to something like a tenth or 100th of these tokens. And this down processing, there is like tools for doing that, the perceiver blocks. But these tokens, they need to interact with each other. And since each token has positional information and information aggregated from the neighbors, it's basically not an information loss, because all information can flow into this down processed bottleneck.
Good, great, thanks. That's very informative. And just a quick question here: if you go to bigger and bigger systems, does the size of this latent space increase? How do you? Can you comment on that?
That is the important question. That's what I want to convey. I think you can design, or we designed this such that this latent space stays the same. So because these perceiver decoders, or this they basically allow you to specify what's the number of tokens you want to have. So it tells you, no matter if I have 1,000 or 2,000 or 10,000 input tokens with dimension whatever, I want to have a latent space of 128 tokens, which with dimension whatever. Because this self-attention, it doesn't mind how long the sequence is, but just these specific tokens you need in the perceiver layer, they can be specified what's the number of them. Then you can come with different number of sequences, different input resolutions, different simulations even, and you can map them to one common latent space.
I see. Okay, good. No, that's understandable. It's very interesting that the errors do not change much based on the experimentations that you did.
I mean, they only change. They're not changing much if it does, like, if it's not resolution dependent in a sense, right? So if you can still resolve all these things which are going on, of course, if you have some turbulence and you sample 2 cores, then of course you're not doing justice for the whole system. But yeah, you know what I mean.
Yes, and just one last question. Would this work in the systems that are like charged and have long-range coordination needed as well? Have you tested on such systems that, for example, a normal summation would not work? You have to do, conventionally, you would do a vault summation.
Yeah, so what I can say, what we are doing is I'm super interested in these particle simulations, and we are scaling these particle simulations up to millions and tens of millions of particles. You have some long range interactions. I personally think that this hierarchical encoding is very well suited to depict all interactions, because in the first step you aggregate locally, in the second step you have these global interactions. So you should in principle be able to resolve all kind of physics which is going on, like over multiple multi-scales. How well this works, I think it needs to be seen, because there's not much work in this direction. I would say the primary focus is to scale this stuff, to get it to large systems, to really show that we can generalize across particle types and number of particles and simulations. Then definitely I think we will encounter some problems, and we will have to go back to the drawing board again and understand how to better encode this.
Yes, that's very interesting. Thank you.
Good questions, yeah.
All right, I think we have time for one more question if anyone else has anything on their mind. Okay, then if we're all good, I can stop the recording.